audiences. And in this, and also in our problem, the counterfactual explanations, ideally they lie on the decision boundaries, so that they could help us to make sense of what a decision boundaries look like. And we use counterfactual explanations to guide users to refine the hypothesis about the model's decision boundaries. So for example, like if the model can propose, a user could propose hypothesis that if the feature A, when the feature value is lower than 0.5, then the model would classify, always give a true classification. And in this case, which is supported by all the observed data, but if we find out the counterfactual explanations, we see that there are some, what we call within boundary counterfactual explanations, which actually opposite to this hypothesis. And this suggests that the rules need to be further refined. And to support this process, we developed a glyph that basically visualizes the distributions of the original data and corresponding counterfactual data. And users could basically to do what-if analysis and to adjust the boundaries to view what is the new counterfactual explanations given the new selections of data. And also like to make it more easier to justify like this, what might be a better decision boundary. So we're using some visual hints like sparkle line, visualize the information gain from a new split. And also we're using the background color to indicate this is entropy. Basically, if it is in a orange background color, it indicates that you should pay attention to it. We have found within boundary counterfactual examples. And so basically, we also show like the individual counterfactual instances. So users could actually view what are the concrete instances that contradict to my hypothesis. And for example, like in this use case, the user wants to understand the diabetes prediction model and proposes an initial hypothesis based on their knowledge that if the patient is younger than 40 years old and whose glucose level is less than 100 millimole per liter, will not have diabetes, which is in blue cast. And so, however, we see that this hypothesis was done through like a drag interaction. And however, we see that in most of the cells, the background color actually are orange, which indicate that this hypothesis is not valid. It's very easy to find the within boundary counterfactual explanations. And so that based on like this, what the user could observe from these distributions and these spark lines, so they could iteratively refine the hypothesis by restricting this hypothesis, basically add more constraints. And what we know is that basically when you add new constraints, you find some of the like conditions that your original hypothesis or your own knowledge do not align with the model's decisions. And for model developers, then you need to pay attention to this subpopulation because model may make wrong prediction to this subpopulation, maybe due to the lack of data. And finally, users could get like to find the true decision boundary of the model, which is already far from its original hypothesis. And through this process, basically, we find a lot of the extra conditions need to be considered when make this prediction and to justify alignment between users' knowledge and the true model decision boundaries. So like in a high-level summary, like in this system, we develop explanation as an interactive process by bringing users in the loop of finding explanations, and which includes two steps. The first step is to allow users to specify their hypothesis, and the second step is to giving user feedback using visualizations. And user do it iteratively by refining their hypothesis and getting new feedback, which will eventually figure out the differences between their like knowledge and the model's true decision logic. Okay, so in this work, we propose a technique based on counterfactual explanations. And now let me introduce a recent work that we want to address two problems. And the first problem is that, so we have shown explanations for structured data, but how about text, especially long text? how could we design interpretable and scalable explanations for long text? And second, in this study, you will see that one type of explanation may not be sufficient. So how can we interactively link different types of explanations to provide better comprehensions? Okay, so then just let me show a hypothetical conversation. So let's see if we ask a model. So we have a patient reporting trouble sleeping and intense pain in the neck. So do you recommend the patient go to hospital? And the model may say, yes, you should definitely go to hospital. The patient should definitely go to hospital. And we want to know like what makes the model make this decision. You can definitely direct ask models or tell me why, and model may give a reasonable self-explanation, which is actually helpful and reasonable, like in most of cases for any users. But if we are more developer, like we want to, the goal is to evaluate whether models are using the proper reasons to make decisions, which these self-explanations is insufficient because the model could lie. I mean, a lot of like recent work have demonstrated that the model self-explanation could be different from the actual decision process of the model, so that models may give a correct self-explanation, but if we change the condition a little bit, the model may make a wrong prediction. So to understand how model actually makes this decision, we have to go back to the original conversation, and we have to figure out what is the factors in this context influences the model's prediction. And while speaking of explainable AI, so a very dominating method is called feature attribution, like lam and sharp, which use a linear function to describe the model's local behavior, something like this. And so basically for each, this sharp algorithm attribute the prediction value to each individual feature. And for each, this attribution value means the feature's weighted average marginal contribution to the prediction, or in layman's language, it indicates the feature's influence. When this value is positive, it indicates that by removing this feature, we will likely see a decrease in the prediction value. And this type of explanation was thought to be useful for text data as well. But is it? So let's see, this could be an explanation, sharp explanation for the text data we just give the model. How should we interpret this explanation? So you may see that actually the word intense pain neck, I mean, these important phrases are highlighted, which looks reasonable, but why do the words patient and repulse, also highlighted, right? So then based on this explanation, can you tell me, like, does the model follow the correct logic to make this prediction? So actually we make a very small scale informal study, and the result we get is quite diverse. Like some people like it makes sense, some people I don't really understand. I think the divergences of humans' knowledge and values is definitely one reason. Another reason is that this type of explanation may not lead to consistent interpretation. So instead of like asking users to guess what they want, like what this explanation may indicate, we want to provide explanations that are more natural and that will lead to consistent interpretations. And to answer this question, let's first see how human naturally do reasoning. So if you have a friend like have this question, and if you want to explain the reasons why you suggest him to go to hospital, you may say that, okay, so the pain is intense, so you have to go to the hospital. Or you say that the neck pain should never be overlooked. Or sometimes you will mention like several symptoms, like the sleep problems accompanied by neck problem. It could be quite severe, so you should go to the hospital. And here I actually highlight the information related to the context. And basically we see that all these claims, all these highlighted text are claims or facts we can get from this context. So human explanations are based on claims or facts, not individual words. So we won't say that this is important because like you have a words reports in your sentences. We instead will see that you mentioned that you have a neck problem. So the claim or the fact of neck problem is a reason for this decision. So this motivated us to build explanations based on the facts or claims. And for example, like in this sentence, like we can extract it, we can say at least 4 claims that the patient reports trouble sleeping, the patient reports pain, the pain is intense, and the pain is on the neck, it's in the neck. And also like this claims or facts are reflected in some of text in this sentence. And like by doing some of the perturbations, we may get some insight about how this model make decisions. For example, like when we report the claim that saying that the patient reports trouble sleeping, we see that the model still make like a recommendation to go to hospital, which indicate that this factor or this claim may not be the most important factor for this prediction. And for example, when we remove the factor saying that the pain is intense, and we observe a flip of the prediction, which indicate that actually the pain is intense, it could be a core reason for model's recommendation. And if we recommend, we replace a claim with a semantically equivalent expression and observe a change of prediction, it might indicate that the model lacks robustness in making these predictions. It may rely on some superficial like features in the text instead of its semantics. So to provide these claim level explanations, we propose 3 questions. And the first is about claim decomposition. So we want to decompose the text into elementary claims. And then we want to do the perturbations by removing and replacing claims on text to produce the counterfactuals. And finally, we want to aggregate these examples and these corresponding results we have to gain a statistically meaningful insight of how model actually works, in making predictions. Okay, so following this roadmap, and so how could we do a claim decomposition? Actually, we find that existing methods mainly rely on human labelers or large language models. And there are three recent works, including 2 from us. Like in the Relic paper, so we're using a language model to extract the claims from the text to provide a claim level uncertainty estimation. And while this language model-based method may be useful and efficient for claim decomposition, but don't forget, we also have a task about creating variations. Like then when we want to rely on language model to create all the variations for us, it could be very costly. So instead, we're considering like how about we make the change of this roadmap. Let's first look at the problem of how to generate meaningful perturbations, and especially by removing part of the sentences. And then like we can naturally get what are the claims in this sentence. For example, like this could be like all the meaningful sentences we can get by removing part of the words in the original sentence. And based on that, we can easily get what are the claims inside of it. And to solve this problem, our approach is based on the dependency grammar, which is a very fundamental problem in linguistics. In dependency grammar, each word is dependent on another word, and which forms the entire sentence into a tree structure. For example, like in the original sentence, this is tree structure. It is dependency structure, and also we want to remove the words from it, and also make sure that the sentences after the word removal are still meaningful. So what we will do is that we remove words from the leaves, right? And we also notice that we are pretty sure that if we remove the subject, like the patient, then we will create an ungrammatical sentence. But if we move a modifier, which is usually doable, I mean, based on this heuristic, we can actually develop the rules of this removal for our removal strategies. And one special case is called the conjunction. And this term, we have to like create a common pseudo parent node for these 2 words for our removal process. So this is the results. So based on the dependency structure, we could actually simplify their structure by combining the trees that cannot be removed. And you see that basically at this stage, we get like 7 nodes, which each of them represent two claim. And using the rules we have, we know how to generate meaningful perturbations by removing these segments. So we using our algorithms, test our algorithms in 5 different data sets to see what is the quality and efficiency in generating the removal-based counterfactuals. What we found is that it's actually still very capable in terms of the grammaticality and the speed. And most of them actually are quite reasonable to humans. So now we have the concrete examples, the counterfactuals we have, and their corresponding model predictions. And from that, we can also run aggregate to get the feature attributions. So how could we provide explanations to help users understand the model's behaviors? So specifically answer the questions of why not, how to be that, and how to still be questions regarding the model's behavior. But before we go to the visualization design, there's one more small question we haven't mentioned. So we know that the model generation is basically it could be a sentence or a paragraph. It's not a binary or structured value. Then how could we actually generate explanations? So to do that, we need to first define an explanation objective that could transform the generated open-ended generation text to a binary value. So for example, like in this problem, what we really interested about is that whether the model will suggest the patient to go to hospital. So we will justify, we will basically add an evaluator to justify whether the generation entails this claim. And sometimes if the problem is closed form, like a multi-choice classification problem, so we may define more simpler evaluators such whether the output contains certain words or not. And we will also run this experiment several times so that we can get a probability that the generation will entails this the facts we are interested. And now let me introduce our system through use case. So actually, this is a use case based on a multi-hop reasoning question. So we basically give a model a long context to describe about a movie and a movie actor, and we ask the model to answer the question of what Canadian actor starred in the film released on June 14th, 2011, based on this long paragraph. And actually, these are the only information required for the model to make a true prediction. And all other informations are noises. So we want to know if the model's prediction logic aligns with the human's like common sense knowledge in this inference task. And using the technique we just described, we actually sampled a lot of perturbations, and each of them is a meaningful paragraph by removing part of the statement in the original context. And of course, we don't have time to go through them one by one because actually it's over 500 perturbations. But luckily, I mean, they are structured. So each claim or each perturbation could be described as a combination of these elementary claims we have introduced. So instead we use a bitmap to visualize each perturbation. So this is a basic visualization we have. So each row indicates a perturbed instance, which is counterfactual, and each column indicate a segment. And so basically each cell, the color of each cell indicates whether these segments is included in this perturbation or not. And users could to view the corresponding text of each perturbation. And for the headers, basically we use the color of the header indicates its attribution value, and orange one indicates a positive contribution, and a blue one indicates a negative contributions. And we also have a column showing the outcome of this variation. And in this case, the outcome indicates the probability that the model responses contain the words which contains the true answer. And we also have a column indicates number of words, which is the supporting column to give users a sense like how much differences has been made of this perturbation to the original sentence. So what questions can we answer using this system? I think the first thing we can do is to conduct a sensitivity analysis. So we can select all the instances with a different outcome, and we can sort them by number of words so that we can see what are the minimal perturbations required to change this prediction. Like for example, like in this case, we see that after removing too noisy information, the prediction already changed, which indicates that this model lacks robustness. And also, since we already know that these 3 segments are sufficient for this prediction, so we could group by these segments, and we can observe that, like in this box plot of the outcome, so most of the outcomes are positive, but there are still several outliers. So specifically, 18 of the 43 perturbations give a wrong prediction, even when we have sufficient information for this task, which indicate that this model is not capable in doing this kind of task. And we conducted a study with a small-scale study with a few users. And what we found interesting in that actually these textual feature attributions are not that interpretable to them, especially for beginners who don't know the semantic meaning of these attribution values. But instead, like they find the counterfactual examples quite useful. Like they want to see the actual task, seeing what words you removed actually change the prediction. And so basically in this work, we revisit the problem of defining interpretable components of text, and which is to be treated as an elementary question in explanations. And conventionally, like people treat each individual word or token as an interpretable component, and we build explanations based on words or tokens. But in our study, so we find it's not sufficient. Instead, we using the claims or facts as individual components to generate explanations. And we see that actually the aggregated explanations of feature attributions we have, they provide an overview. But for many users, like the people who don't have strong technical background in explainable AI, don't find them intuitive enough. So we want to interactively link them with concrete counterfactual examples, which show the details of explanation. And these counterfactual examples are justifiable and interpretable to all the audiences. So by interactively linking these 2 types of explanation in 2 different levels of abstractions, users could get a better understanding of how the model works. And also, we actually built a tool that make this system usable with Jupyter Notebook, and if you're interested, you can check it. Okay, and now let me give a summary of today's talk. I would like to summarize through 3 dimensions. And the first question we targeted is the why interactivity. And so our argument is that people usually don't build their mental models from scratch. So we should build explanations on what people already know and actively involve humans in the loop. And so how do we design interactions? So in the 2 works I presented, it demonstrated two patterns. The first pattern is, I call it hypothesis testing pattern. So basically, we want to support users to specify their hypothesis and provide feedback to validate their hypothesis using visualizations. And the second pattern, I call it overview and details pattern, that we're using aggregated explanations like feature attributions to provide an overview, and we're using concrete counterfactual examples to show details in demand. And by interactively linking these 2 types of explanations, users could gain better comprehension. And the last question is about what do we get from interactive explanations? So what we get is numbers of charts, which is definitely not correct. instead of number of charts, what we actually eventually want to get from these explanations is a better assessment of the alignments between model behaviors and human knowledge. And that is my presentation. Thank you.
Yeah, thanks a lot, Furui, for the great talk. See some applause also in Zoom. I think with that we can get to the question part. So for the people on Zoom, please either just unmute yourself or post your question in chat. I see no raised hands yet, so I have a couple of questions actually, so maybe I can kick things off. So you mentioned hypothesis testing, and it seems that in order to apply that for the large language model, especially, you had to phrase the questions as a binary choice question in some way so that you can use a binary evaluator function. If I understood it correctly?
Well, so basically, I mean, the case we showed is a special case that the question is a multi-choice, classification problem, but it could be generalized to any problem, because if we want to explain something, naturally we'll divide the outcome into two categories, like a desired one and undesired one. So like, for example, like you want to explain like why this you recommend this patient to go to hospital, like we will naturally like already classify the outputs into two sides. One is that we're recommending the patient go to hospital, another is the rest of them. So I would say that it could be generalized to any problems as long as you have a clear explanation objective.
And if the question is more open-ended, so not like, should I go to hospital, but let's say, what should I do? And the LLM can answer any type of response. How could I still somehow apply this without splitting it into like two binary things? But maybe
that's an interesting problem. So basically, as I said, users have to have a explanation objective. So you have to be clear about what model behaviors you are interested. And let's say if it's open-ended question, but you have to, have a hypothesis, like, okay, so I want to figure out whether the model will recommend me to go to museum or not. If we have this question in mind, then we can naturally divide the potential outcomes into two categories: go to the museum or the others, and then we can get explanations.
And in your work, these explanation objectives are fixed for certain tasks in the beginning?
Our system is basically, is decided by users. Like users could be using whether the explanation contains some words or whether the explanation logically entails some statement. This should be is basically defined by users.
So I could also construct my objectives only once I already received the response and say, okay, why does this word show up in the LLM response, for example, or this phrase? This would be possible.
That is an interesting extension actually. So I can imagine like in a more ambiguous and open-ended question like this explanation objective are iteratively found. Like it may not be that clear at the beginning, but through like iterations, people may have a better question in their mind. So our system, we currently don't. This is a one-time thing, but it could be an interesting extension.
I see that there's a question on Zoom. So Benjamin asks, how would the temperature used in inference of the LLM affect the perturbation result? Did you test that in your study?
So yeah, in my study, so basically I use the default temperature setting. I think like the temperature will basically you can imagine like if temperature have a different value, then like we may stick a different distribution of this outcome, right? If like in a special case, like the model score will always be consistent, then we have only 1 or 0. It still may work, but yeah, technically it will work, but it may lead to different interpretations.
Would you expect these like kind of factual questions where I ask for some specific actor? Would you expect that the model performs worse with higher temperatures because hallucinations might be more likely, or is it not as simple? That's good.
You mean like if the model is like when models may is uncertain about its prediction, then like how models response or accuracy will I mean like from statistical perspective, like if we are doing a testing on a data side, I don't think it will influence the overall performances. But for each individual instance, of course, like if by having a lower temperature, then we have what diverse, like we can estimate this confidence in a value between 0 and 1, and which gives us more information. But if to say super high temperature, then also will be obviously consistent. Then like from single instance prediction, then we get this information about that.
Mm-hmm.
Very general question, and this was about text and large language model reasoning. Are you also interested in images and reasoning of large multimodals? How would that extend?
Yeah, I mean, I think for vision models, I mean, still like an elementary question is about what is the elements for explanation? Do we want to make explanations based on pixels, or do we build explanations based on like, for example, like the objects or like this, some high level concepts there? So
I'm talking about large model vision reasoning, like when you use ChatGPT, post an image, ask a question about the image content. So this is using a vision reasoning model.
yeah, I mean, like still like if the input is like the input is the image, right? It's the image plus a text, and we want to like figure out, for example, which part of the image like influence the text. We still face a problem of defining the interpretable components here. So like, how do we want to generate explanations? Do we want to generate explanations by pixels, or do we want to generate explanations like by some high level objects or concept in the image? And I think that this problem still exists. And it remains a challenging problem in defining interpretable components in text. Does it answer your question?
So do I understand this correctly? If I wanted to apply a similar concept to images, I would need something that does for images what you do for the text, to create many instances of still meaningful sentences that you can test.
I mean, like this is one approach. Like if we don't have any assumptions to the model structure, then like using like these variations to testing, this is a common approach. Like using
this is what is done for line image based, you do super pixel based.
Yes,
sampling
yes,
or
yes,
something like that.
yes. And also like if we know the model is differentiable, then there are different approaches using the gradient.
Yeah, that's based on classification, and the transformer-based model that actually does reasoning.
I think there you would probably still have to have the objective similar to the text-based case, where you need to define the explanation objective.
I would say that, I mean, the reasoning, for them, like the models we want to build a self-reasoning model is different from explaining a classifier. So they are definitely two different objectives. So, I mean, if we want to explain a reasoning model, then the first thing still is to defining an explanation objective. So what do we want to reason about this reasoning model, right? So like, for example, like this is a, if I understand it correctly, that's for example, like for a scene understanding model, and you tell me this is a living room, and like, why do you think this is a living room, right? This is the questions, the explanation questions we want to answer. And these explanations could be based on like different levels of components. Like this is a living room because there's a sofa there. This is a living room because we see actually these areas of this image is very influential to the prediction.
It requires you to understand the image. You understand there's a sofa there without getting that information from the large model. You need to understand there's an image in there. I mean, before you deal with text, and you can of course look at it.
But that's what you just said. You could also, without understanding that there's a sofa, you could say this area was important for
how do you
you.
get this? How do you get the understanding there is a sofa without going for the reason?
I mean, like it's just I mean, like ideally, I mean, just theoretically, is to prove that this sofa concept contributes to this prediction. Then we need to like create variations with and without sofa. you can treat it as a causal, analysis problem, right? So we have two sides of data with and without SOFA, and we see that when we have the SOFA, like the probability of predicting it's a living room goes higher, then it indicates that this factor, this concept plays an important role in this prediction. And so usually, but this is usually very challenging. Like if we want to ensure diversity of the data set when we interpret in a whole, like we want to prove it as a global explanation. So usually we only look at a small local region, like for example, like for this type of image, or like and in this neighborhood, we can pretty sure that the concept of SOFA plays an important role through these counterfactuals.
So thinking about explanations, like in the context of traditional models that are usually trained for a specific task, for example, classification. When we think about the input, they take their input and they process it somehow to extract some features and just make a classification decision for these features. And these scenarios, maybe I would be more satisfied to have an explanation that's based on the input, saying that these inputs are the inputs that led to the classification decision. However, I'm thinking about the LLMs maybe in a different way. So the prompt is not actually, maybe it's not the input that would be, that the task would be applied on, but instead it's a kind of a piece of text that leads the model's activations in a specific way. So it's like it focuses on a specific part of its knowledge learned in training, and it just bring up a context in order to generate a response at the end. So do you think in order to answer this why question, input-based explanations is enough, or would an approach that links the reasoning steps with this input explanation, would it be more complete?
Based on what you mean, you're asking like why explainable, like observing from its outside is sufficient for answering the why question. Is that your question? Well, it depends on like how you define a sufficient answer for a why question. So basically, if we want to theoretically prove that some factors plays an important role like to the model's prediction, it is super challenging. So no matter of black box explanations or mechanism interpretabilities, we rely on observations. So like we see that, okay, so based on the samples we have sufficient samples, and in these samples we figure out that actually these factors plays an important role. It has strong causal effect to the prediction, and this is how we figure out. This is how we approach this question, but I'm not quite sure about this, how this question is related to the why question in your mind.
Yeah.
I think there are no more questions, and so I have one maybe final question, unless anything else comes up. Who do you see as the target users for these two tools, and who took part in the studies, in your feedback loops? I would be interested in that.
Yeah, so basically what we are expecting, the target users, meaning including the model developers or the domain expert who have like a basic knowledge of that. And the reason is that, so, of course, for like ordinary people, for end users, we are not expecting them to really figure out how the model work. There are much more easier and cheaper ways to to explain or to influence their trust. But for model developers or sometimes for domain expert, when we want to use a model in my own field, I need to first test it and make sure that it aligns with my knowledge and my values, right? So in this case, you may need a tool that could give you the insight in terms of alignments between your knowledge and the model's behavior. And that is the expected scenarios of the tools I develop.
that brings me to two quick follow-up questions. So
Okay.
one is how do I measure this alignment? Like yeah, I learn about the model, but can I actually somehow quantify that? Or is this only my own thought, okay, that I feel like now I understood the model better?
I mean, like in terms of the quantification, like for example, like we already in this case which I just showed, so we already know like these three conditions are sufficient, right? And so we samples like in the counterfactuals, like when of this instance that satisfy these three conditions, we see that 13th, like 18th of the 43 instances have a different prediction, which indicates like this. This model misprediction or this lack of robustness is a common problem. I mean, for this instance as well.
Mhm. So you can definitely quantify this part about the model performance, but how well that aligns with the user's mental model of how the model should behave, that is kind of encoded in the objective,
I mean, like,
in the
so
explanation
basically,
objective?
yeah, I mean, like if we treat like each perturbation has the same equality, I mean, like a same like equality of viewing them. So basically we see that over like 13 of the 48, I mean 18 of the 43 times, we will see a misalignment in terms of the human's decision and the model decision, which I think is qualify this misalignment. Does it make sense?
Yeah, I think so. And I think the other question I will take offline. We can talk about it now. If we can wrap things up. Thanks for the talk, Furui. Thanks for coming here in person. It was great to have you. And thanks everybody for participating and listening. Let's thank Furui once more.